Good morning, everyone. I'm excited to welcome you to today's presentation. We'll be exploring the fascinating topic of the dual nature of radiation and matter. This is a fundamental concept in physics that helps us understand how particles and waves behave in different situations. Over the next few slides, we'll cover the key principles, historical developments, and practical implications of this intriguing subject. Let's dive in and discover the dual nature of radiation and matter together. Let's explore the key topics related to the photoelectric effect and its foundational concepts. We start with the de Broglie wave, which introduces the idea that particles like electrons exhibit wave-like behavior. Moving on, we focus on the verification of the laws of photoelectric emission, mainly based on Einstein's photoelectric equation, which explains how light causes electrons to be emitted from a material. Next, we consider the effect of frequency, emphasizing that the energy of the incident photons depends directly on their frequency, not their intensity. This is crucial in understanding the photoelectric effect. We then look at the photoelectric effect itself, how photons eject electrons from a surface when certain conditions are met. The Davison and Germer experiment is a landmark in demonstrating the wave nature of electrons, confirming de Broglie's hypothesis. Speaking of photons, they are packets of energy, which plays a central role in explaining the photoelectric effect. Einstein's photoelectric equation quantifies this, linking the energy of emitted electrons to the photon energy minus the work function of the material. We also examine the effect of collector potential, which influences the flow of photoelectrons and helps us analyze the current generated. Moving toward applications, we see how photoelectric cells are used in various fields, from light meters to solar panels. De Broglie wavelength for electrons is another fascinating concept, showing that electrons have wave-like properties with a specific wavelength depending on their momentum. We revisit Einstein's equation to reinforce our understanding of how photon energy relates to electron emission. Furthermore, the effect of light intensity on photocurrent is explained. While intensity affects the number of emitted electrons, it doesn't change their maximum kinetic energy. The laws of the photoelectric effect define the fundamental principles governing this phenomenon. The experimental study of the photoelectric effect provides the empirical evidence that supports these theories. Finally, we look at the origin of the theory, which combines quantum ideas to explain phenomena that classical physics couldn't, leading us to important real-world applications of this effect. All these points connect to deepen our understanding of how light interacts with matter at a quantum level, which is the core theme of this presentation. The idea of duality actually started back in the 17th century during a debate about the nature of light and matter. At that time, two major theories were competing. Christian Huygens believed that light was made up of waves, while Isaac Newton argued that light consisted of particles. These ideas laid the groundwork for a fundamental question in physics. Over the years, many brilliant scientists, including Max Planck, Albert Einstein, Louis de Broglie, Arthur Compton, and Niels Bohr, contributed to our understanding. Their work eventually led to the current scientific view that all particles can also exhibit wave-like behavior, and vice versa. This duality is a core concept that underpins much of modern physics and helps us better understand the universe at its most fundamental level. Let's explore how different phenomena involving radiation can be understood based on its dual nature. First, consider phenomena like reflection, refraction, and dispersion. These are cases where radiation interacts, but neither with matter nor with other radiation. They can be explained by recognizing the dual nature of radiation, specifically, that it has both wave and particle characteristics, allowing us to understand these phenomena from either perspective. Next, look at effects such as the photoelectric effect, Compton scattering, and pair production. These are instances where radiation interacts directly with matter, and they are best explained purely through the quantum or particle nature of radiation. This is where the particle aspect becomes essential to understanding what's happening. Finally, phenomena like interference, diffraction, and polarization involve interactions within the radiation itself, meaning waves interacting with waves. These can be fully explained only by considering the electromagnetic wave nature of radiation. Connecting this to our overall theme, understanding these different interactions helps us appreciate the complex dual nature of radiation, which is central to many concepts in modern physics. Let's talk about the work function, which we denote as F0. This is the minimum energy an electron needs to escape from the surface of a metal, starting from rest. Essentially, it's the energy required for an electron to just break free without any initial velocity. The work function varies depending on the type of metal, typically ranging from about 2 eV to 6 eV. Remember, 1 electron volt, or eV, is equal to 1.602 times 10 to the power of negative 19 joules. Now, every metal contains free electrons. These electrons are quite mobile. They can move from one atom to another within the metal. But even though they are free to move internally, they can't leave the metal's surface on their own. That's because of the electrostatic attraction from the positive nuclei inside the metal, which acts like a barrier holding the electrons in place. However, if we supply enough external energy to these free electrons, their kinetic energy increases. Once they gain sufficient energy, they can overcome that surface barrier and escape the metal. This process of electrons leaving the surface when given enough energy is known as electron emission. So, in summary, electron emission occurs when free electrons in a metal gain enough energy, equal to or greater than the work function, to cross the surface barrier and leave the metal. This concept is fundamental in understanding phenomena like photoelectric effects and various electron emission processes. In this method, a high-velocity beam of primary electrons strikes the metal surface. The intensity of secondary emission depends upon the emitter material, mass, and energy of bombarding particles. The ejected electrons are called secondary electrons. Next, we have secondary emission, where a strong electric field, meaning a high positive voltage, is applied at the metal's surface. This field pulls the free electrons out of the metal because of the attraction exerted by the positive charge. The stronger the electric field, the more electrons are emitted. These ejected electrons are known as field electrons. Moving on to photoelectric emission, this occurs when light falls on the metal's surface. The energy from the light is transferred to the free electrons inside the metal, giving them enough energy to leave the surface. The more intense the light beam, the greater the number of electrons ejected. These are called photoelectrons. Finally, we have thermionic emission, which happens when the metal is heated to a very high temperature, around 2500 degrees Celsius. At this temperature, the thermal energy provides electrons with enough energy to escape the metal surface. The number of electrons emitted depends on the temperature. The higher the temperature, the more electrons are emitted. These are called thermal electrons. These different methods of electron emission are fundamental to understanding how electrons are generated and utilized in various electronic devices and technologies. Let's explore the relationship between work function, threshold frequency, and threshold wavelength. The equation phi equals h times vo, which also equals hc divided by lambda max, captures this connection. Now, the threshold wavelength, lambda max, is the maximum wavelength of light that can eject photoelectrons from a metal surface. In simpler terms, if the light's wavelength is longer than this, it won't have enough energy to free electrons. Conversely, the threshold frequency, vo, is the minimum frequency of light needed to eject those electrons. This concept was first discovered by Heinrich Hertz back in 1887 during his experiments with electromagnetic waves. The electrons emitted during this process are called photoelectrons, and the current they produce is known as the photoelectric current or photocurrent. This entire phenomenon, the emission of electrons from a metal's surface when exposed to light of a suitable frequency, is what we call the photoelectric effect. It's a fundamental concept that links the energy of light to its ability to release electrons from materials, connecting nicely to our overall discussion of quantum physics and the particle-like behavior of light. All right, let's look at the key components of this setup. We have the metallic anode, labeled as A, which plays a crucial role in collecting the photoelectrons emitted from the cathode. When light of a suitable frequency strikes the metallic cathode, labeled as C, it causes photoelectrons to be emitted due to the photoelectric effect. These emitted electrons are then attracted towards the positively charged anode, creating a photoelectric current. Next, there's the quartz window, W, which allows the light to pass through without interference, ensuring the photons reach the cathode effectively. This setup was practically studied by Philip Lenard, who conducted experiments to understand this phenomenon better. As shown in the diagram, his experimental arrangement includes all these components working together to demonstrate how light can eject electrons from a metal surface. Understanding this setup helps us grasp the fundamental principles behind the photoelectric effect, which was pivotal in advancing our knowledge of quantum physics. It clearly illustrates the direct relationship between light energy and electron emission, connecting beautifully to the broader theme of how light interacts with matter. Let's talk about how photocurrent relates to intensity. When the intensity of light increases, it means more photons are hitting the surface. As a result, the number of electrons emitted also increases. This increase in emitted electrons leads to a higher photocurrent. Now, it's important to remember that current is essentially the number of electrons passing through a cross-section in a given amount of time. So, as more electrons are emitted due to higher intensity, more of them flow through the circuit per second, increasing the current. This connection between intensity and photocurrent is fundamental because it shows how the amount of light directly impacts the flow of electrons, which is key to understanding the photoelectric effect and how light energy translates into electrical energy. So, the stopping potential depends on two main factors: the frequency of the incident light and the work function of the material. As we see here, the stopping potential V stopping is given by the equation HV, F0, divided by E, where HV is the photon energy and F0 is the work function. This means that the maximum kinetic energy of the emitted electrons is related to the photon energy minus the work function. In fact, we can express this as Ke max equals HV minus EV stopping, which also equals HV minus F0. And if we multiply the stopping potential by the charge of an electron, EV stopping, it equals Ke max. Now, if we keep the collector voltage negative, it will repel the emitted electrons. At a certain negative potential, all electrons will be repelled, and the photocurrent drops to zero. We call this specific potential the stopping potential. Next, let's look at how the current behaves in relation to the collector potential. Initially, as we increase the collector potential, the current increases because more electrons are being collected. But after a certain point, the current reaches a maximum and saturates. It becomes constant. This saturation occurs when the number of emitted electrons equals the number of electrons being collected. That maximum current is what we call the saturated current. Finally, remember that the collector potential's main purpose is to help in collecting the emitted electrons efficiently. It's an important aspect of understanding how photoelectric cells work and how we control and measure the flow of electrons in these systems. Let's look at the graph showing the relationship between frequency and stopping potential. You'll notice that it's always a straight line, which indicates a direct proportionality. This line also tells us something important. There's always a minimum frequency, called the threshold frequency, below which no photocurrent is produced. Now, when the incident light has a fixed intensity, the photoelectric current doesn't depend on the frequency of the light, as long as it's above that threshold. The saturation current, which is the maximum current when all emitted electrons are being collected, remains the same for all frequencies greater than the threshold. This highlights a key concept in the photoelectric effect. Once the frequency exceeds the threshold, increasing it further doesn't increase the current. Instead, it just affects the stopping potential needed to halt the photoelectrons. So the frequency essentially determines whether electrons are emitted at all. But once that threshold is crossed, the current is governed by the intensity, not the frequency. This understanding is fundamental to the quantum nature of light and the photoelectric effect. The photoelectric emission is an instantaneous process, which means that as soon as a photon of suitable frequency hits the material, photoelectrons are emitted immediately. There's no delay involved. Now, for a specific metal, there's a minimum frequency threshold, called the threshold frequency, that must be met or exceeded for photoelectrons to be emitted at all. If the frequency of the incident light is below this threshold, no electrons are ejected, regardless of how intense the light is. Once you go above that threshold frequency, the maximum kinetic energy of the emitted photoelectrons actually depends on how high the frequency of the incident light is. So, higher frequencies, above the threshold, give the electrons more energy. And for a given metal and a fixed frequency of light, the rate at which photoelectrons are emitted, that is, the photoelectric current, is directly proportional to the intensity of the incident light. Essentially, brighter light results in more electrons being emitted per unit time. These key points help us understand the fundamental nature of the photoelectric effect, which is crucial in connecting classical and quantum physics concepts. Now, let's look at what happens after the photon transfers its energy to an electron. The remaining part of that energy is actually used to give the emitted photoelectron a velocity, which we call v. This velocity corresponds to the maximum kinetic energy of the photoelectrons, which is given by the expression half the mass times the square of this maximum velocity, or a half mv2 max. Here, m stands for the mass of the photoelectron. But not all of the photon's energy goes into this kinetic energy. A part of it is needed just to help the electron overcome the surface barrier of the metal and escape from the surface. We call this part of the energy the work function, denoted as F0, which equals HVO. Essentially, it's the minimum energy required for an electron to leave the metal surface. Now, recalling that the energy of each photon is given by E equals h nu, Einstein used this idea to explain how photoelectric emission actually happens. According to his theory, when photons of a certain energy hit a metal surface, they transfer their energy directly to the electrons inside the metal. This concept is rooted in Planck's quantum theory, which tells us that light isn't just a wave, but is emitted in discrete bundles of energy called photons. These photons carry quantized energy, which is fundamental to understanding the photoelectric effect and how energy is transferred at this microscopic level. So, in summary, when light of a certain energy strikes a metal, photons transfer their energy to the electrons. Some of that energy is used to get the electrons out of the metal, overcoming the work function, and the rest becomes the kinetic energy of the emitted electrons. This process is the foundation of Einstein's photoelectric equation, which elegantly describes the relationship between photon energy, work function, and the kinetic energy of photoelectrons. This relation is called Einstein's photoelectric equation. It describes how the maximum kinetic energy of ejected electrons relates to the energy of the incident photons. The equation is Kmax equals h times nu minus vo. Here, Kmax represents the maximum kinetic energy of the electrons, h is Planck's constant, nu is the frequency of the incident light, and vo is the threshold frequency required to eject an electron. You can also see it expressed as Kmax equals HVO plus 1/2 mv max. This shows that the kinetic energy of the ejected electron depends on the energy of the photon minus the work function, which is the minimum energy needed to free an electron from the metal. If we rewrite the equation in terms of energy, it becomes h nu equals F0 plus 1/2 mv max. In this form, energy of the photon is equal to the work function plus the kinetic energy imparted to the electron. This highlights a key point. The energy of the photon is used to overcome the work function, and any excess energy is converted into the kinetic energy of the emitted electron. And according to the law of conservation of energy, the total energy from the photon gets distributed between overcoming the work function and providing kinetic energy to the electron. This equation is fundamental because it confirms that light behaves as quanta of energy, and it explains how electrons are emitted when light hits a metal surface, which is a core concept in understanding the photoelectric effect. Now, let's look at photoelectric emission in more detail. First, it occurs due to a collision between a photon and an electron. Because of this direct interaction, there can't be any significant time lag between the photon hitting the surface and the emission of a photoelectron. In fact, experiments show that this process is almost instantaneous, with a delay of only about 10 to the power of -8 seconds. Moving on, we see that the maximum kinetic energy of the emitted photoelectrons, which we denote as a half MV2 max, is proportional to the frequency of the incident light, nu. This is because Planck's constant, h, and the threshold frequency, vo, are constant. So this relationship tells us that the kinetic energy increases linearly with the frequency of the light. Next, since each photon can emit only one electron, the number of photoelectrons emitted per second is directly proportional to the intensity of the incident light. In other words, increasing the light's intensity will increase the number of electrons emitted, assuming all other factors stay the same. And finally, if the frequency of the incident light is less than the threshold frequency, nu vo, then the maximum kinetic energy becomes negative, which isn't physically possible. This means that for photoelectric emission to occur, the frequency must be greater than the threshold, or nu vo. All of these points tie back to Einstein's photoelectric equation, which helps us verify the fundamental laws behind this phenomenon. When a radiation of suitable frequency strikes the cathode, photoelectrons are emitted. These photoelectrons are then attracted towards the anode, which is maintained at a positive potential relative to the cathode. This setup causes a current to flow when the radiation hits the metal surface, and we can measure this current using a microammeter. A device that converts light energy into electrical energy is called a photoelectric cell, or sometimes a photocell or electric eye. These devices are crucial in various applications, which we'll explore further. Understanding how the photoelectric effect works helps us see its practical uses, from light sensors to automatic lighting systems. It's fascinating how a simple exposure to light can generate electrical energy, and this principle has a wide range of technological applications. Now, let's explore some of the key applications of photoelectric cells. These devices are incredibly versatile and play a vital role in many fields. For instance, they are used to identify minor flaws in metallic sheets, ensuring quality control in manufacturing. They also help determine the opacity of solids and liquids, which is important in various scientific and industrial processes. Another common application is sorting materials based on their shades, which is useful in recycling and mineral processing. Photoelectric cells are also used to monitor and control the temperature of chemical reactions, helping maintain optimal conditions. Interestingly, they are involved in fundamental physics experiments, such as the determination of Planck's constant, by studying the photoelectric effect. In photometry, they compare the illuminating powers of two sources, which is crucial in designing lighting systems. They're also used in street lighting automation, switching lights on and off without manual intervention, which saves energy and enhances safety. Additionally, photocells help measure the temperature of stars and analyze their spectra, contributing to astronomical research. They are integral in security systems, like burglar alarms and fire alarms, providing reliable detection. In everyday technology, photocells are employed in counting machines, sound recording, and video recording devices, enhancing accuracy and automation. Lastly, photoelectric cells are fundamental in television cameras for broadcasting scenes and are also used in phototelegraphy, enabling quick transmission of images. Overall, these applications highlight just how essential photoelectric cells are across science, industry, and everyday life, connecting their fundamental principles to practical uses that improve efficiency, safety, and our understanding of the universe. All photons, regardless of how bright the light is, have the same energy. What changes with increasing intensity is simply the number of photons present, So more intense light means more photons, but each photon still carries the same amount of energy. The energy of a photon can be described by the equation E equals h times nu, which is also hc divided by lambda. Here, h is Planck's constant, nu is the frequency, c is the speed of light, and lambda is the wavelength. Similarly, the momentum of a photon is given by h divided by lambda. When a photon collides with a particle, the total momentum is conserved, just like in any other collision. But it's important to note that some photons may disappear during the collision, so the number of photons can change afterward. Photons are massless, which is quite a unique property. Their energy and momentum depend solely on their frequency or wavelength, not on mass. Another key point is that photons are electrically neutral. This means they are unaffected by electric or magnetic fields, which makes sense given their neutrality. In summary, photons are packets of energy that behave in fascinating ways. They have no mass, are neutral, and their energy and momentum are linked to their frequency. All of these characteristics are fundamental to understanding their role in the broader context of light and quantum physics. Let's look at the expression for de Broglie wavelength, which is lambda equals h divided by mv. This formula tells us how to calculate the wavelength associated with a moving particle, where h is Planck's constant, m is the mass of the particle, and v is its velocity. Now, if instead of a photon, which is massless, we consider a material particle that has mass m and is moving with velocity v, the equation adapts accordingly. According to Einstein's theory, the energy of a photon is given by E equals mc squared. But remember, for a photon, this energy can also be expressed through quantum theory as E equals h nu, which is also hc over lambda. So, putting these ideas together, we arrive at the expression for de Broglie wavelength, which is lambda equals h divided by mv. De Broglie proposed a fascinating idea. A moving material particle can be associated with a wave. This means that a wave can actually guide the motion of the particle itself. The waves linked with these moving particles are called de Broglie waves or matter waves. This concept was groundbreaking because it bridges particle physics and wave physics, showing that matter exhibits wave-like properties under certain conditions. In essence, de Broglie's theory helps us understand the wave-particle duality, which is a cornerstone of quantum mechanics and critical to the overall understanding of atomic and subatomic behavior. Let's focus on electrons for a moment. When we're talking about the charge of an electron, denoted as E, the kinetic energy K can be expressed simply as E times V, where V is the applied voltage. This is a key point because it links the energy an electron gains directly to the voltage it moves through. Now, the kinetic energy isn't just an isolated concept. It's related to the momentum of the electron as well. As we've studied earlier, there's a fundamental relationship between an object's momentum and its wavelength, which is the basis for wave-particle duality. This brings us to the de Broglie wavelength for electrons. Remember, de Broglie proposed that particles like electrons exhibit wave-like properties, and their wavelength is inversely related to their momentum. This connection is crucial because it allows us to analyze electrons not just as particles, but as waves, opening up new ways to understand their behavior at the quantum level. So, in summary, for electrons, the kinetic energy depends on the voltage, and this energy is directly tied to their momentum, which in turn relates to their wave nature through the de Broglie wavelength. This concept is fundamental in bridging classical and quantum physics and helps explain many phenomena at the microscopic scale. Now, let's wrap up with some key takeaways. First, the de Broglie wavelength is independent of the charge of the particle, which means whether the particle is charged or neutral, the wavelength calculation remains the same. This highlights that matter waves are fundamentally different from electromagnetic waves. Speaking of which, matter waves, like electromagnetic waves, can travel through a vacuum, but unlike mechanical waves, they are not dependent on a medium. Additionally, if a particle is at rest, its de Broglie wavelength becomes infinite, making it impossible to visualize such a wave. It's a fascinating concept that shows the limits of wave-particle duality. Also, it's important to remember that matter waves are not electromagnetic waves because they are not produced by accelerated charges. Now, regarding how the wavelength relates to the particle's properties. The de Broglie wavelength is inversely proportional to the particle's mass. So, heavier particles have smaller wavelengths compared to lighter ones. Similarly, the wavelength is also inversely proportional to the particle's velocity, meaning that as a particle moves faster, its wavelength gets smaller. Altogether, these points reinforce the idea that wave-particle duality is a fundamental concept in quantum mechanics, connecting the behavior of particles with wave properties in a very elegant way. Let's take a closer look at the Davison-Germer experiment. In this setup, a beam of electrons emitted from an electron gun is directed at a nickel crystal, which is cut along the cubical axis at a specific angle. As these electrons hit the crystal, they scatter, and the scattered electrons are detected by a detector that can be rotated freely to different angles. What's fascinating is that by changing the voltage applied to the electron gun, we can vary the energy of the incident electrons. When we do this, we notice that the intensity of the scattered electrons reaches a maximum at a scattering angle of 50 degrees, specifically when the accelerating potential is about 54 volts. Now, why is this experiment so important? Well, it was conducted by Clinton Davison and Lester Germer in 1927, and it provided critical evidence supporting the de Broglie hypothesis from 1924. This hypothesis suggested that particles like electrons, which we usually think of as matter, also have wave-like properties. This experiment didn't just verify de Broglie's idea, it demonstrated the wave-particle duality, one of the core concepts of quantum mechanics. It also marked a significant step in developing the Schrödinger equation and understanding the quantum nature of reality. So overall, the Davison-Germer experiment was a groundbreaking moment that bridged the gap between classical and quantum physics, confirming that particles can indeed behave as waves under certain conditions.